Thank you, Henny, and good morning, everyone. And thanks, Clyde, for turning up this morning. I hope you've got your gen set working, but and I can't hear it in the background, though. Just by way of introduction, Clyde is a geologist by profession. He's a registered natural scientist, a fellow of the Geological Society of South Africa, and a member of the South African National Energy Association, and equally a founder member of the South African Energy Storage Association. Clyde has more than 45 years experience in the Resources Centre, and at one time or other has been a mill superintendent for Falconbridge in Namibia. Maybe that gives him or gives us some idea of his vintage. A lecturer at Rhodes University. He was involved in the MSc program there, which many of us will have known about. And he's also done time at Fort Hare University. Today, he is a consultant specializing in resource assessment and techno-economic evaluation of resource projects. He also is involved in an exploration fund and an energy fund founder member. So he's going to talk to us today about his views on the challenges that this country faces in its whole energy provision. And we look forward to your presentation, Clyde. Thanks for making yourself available.
Thanks for that kind introduction, John. So I'm going to be primarily trying to look at what the future holds in our electricity supply industry. So I think we all should be, and if we're not, we definitely should be, are familiar with the issues and the problems surrounding our current electricity supply. So I'm going to focus then rather on looking at what the potential future holds and how exciting that future is from my perspective anyway. So it's always good to start off by reminding ourselves where our planet is headed towards. We're headed towards terra incognita if we carry on as we are. And we're all aware of the effects of global warming, of the effects of pandemics, and we really are at the end of being able to operate in a sense of business as usual. One of the diagrams I like to kick off with when I'm talking about energy is this wonderful thing called a senki diagram. And I like using the one for the US for 2018 because it just turns out that the amount of energy they used in 2018 was 101 quads, which I think is quadzillion BTUs or something like that. But the reason I like using it is because it's 101, everything you read on this diagram can more or less be interpreted as a percentage. So if it says petroleum 36.9 quads, it's kind of like about 36%, and it's just convenient. And all I really want to show with this is this notion of plotting out the American energy usage was introduced, I think, in the 70s, when we also had an energy squeeze, if any of you can think that far back. And I think it might have been Jimmy Carter or someone, or Ford, or one of those guys who said he wants to see a plot of where all energy comes from in the US and where it all goes to. And this is really a summary of that plot. But the data that's collected in the US is so accurate that they can tell how much fuel or diesel or petrol was used to take school children to school in government buses versus the fuel used to take people to school in private cars. So it's a very detailed diagram. But the key thing I want to point out about it is that on the left-hand side, you've got your primary energy inputs. And on the right-hand side, you've got right on the right-hand side, you've got energy services and wasted energy. And what I really want to point out here is that 2/3 of the primary energy that's input into the system is wasted. It doesn't do anything useful. So quite a nice one to look at is electricity. You can see in the US, there's coal and nuclear and natural gas, a little bit of hydro and a smidgen of solar and wind. But you'll see that electricity generation only, 38.2 quads go in, and 12.9 quads go out, and the rest is waste energy. And that's just thermodynamic inefficiency of burning of anything really, and trying to produce electricity from it. So I've tried to construct one for South Africa, an energy mix. And so once again, on the left-hand side is our primary energy inputs. Petroleum is the biggest primary energy input. Coal, nuclear. Note the nucleus is 42. These are actually in terawatt hours. It says 42 terawatt hours, and people might question that and say, gee, I thought Overberg only produced about 15 terawatt hours. And the reason is that I'm counting the primary energy from the decay of uranium, which eventually, when it gets translated into electricity, also only has about a 30-something% efficiency. So the actual energy input from the uranium is about 3 times as much as the eventual electricity that comes out. And once again, one can see that about 66 or 2/3 of South Africa's energy goes to waste. Also useful looking at transport propulsion. Current cars range between about 20 and 30% efficient. I think diesel is about a really good efficient diesel car will give you a 30% energy conversion from burning of diesel to kinetic energy, and I think petrol will give you about 20%. And those who have owned diesel and petrol cars will recognize the different fuel consumption numbers mirror that more or less. Now, here's a thing that comes from Mark Jacobson at Stanford University, looking at estimating 2050 global energy costs. If we carry on at business as usual, and when I say business as usual, I'm not excluding the switch to different forms of sustainable energy. I'm saying there will be switching, but we kind of carry along at a sedentary kind of rate. We're switching out to other sources, but we're not really doing it with any great urgency. The world will spend about $18 trillion on energy by 2050 if we go along business as usual. If we switch to an energy system made up entirely of solar, wind, and storage by 2050, we will spend about $7 to $8 trillion. And that difference just simply reflects the thermodynamic inefficiency of burning fossil fuels and ending up with 1/3 of useful energy. So it's a straight relationship relative to that Sankey diagram. So we could do it if we switch to completely renewable, 100% solar, wind, and storage by 2050. And we can discuss what forms of storage. It's not necessarily all battery energy storage. We can come in at about 40% of the cost of a business as usual model. But here's the bit that's really scary. Business as usual, the estimated health cost of energy, this is on air quality globally. So it's air quality from burning coal, from burning fossil fuels in motor vehicles. The estimated health cost of energy by 2050 is actually greater than the cost of producing energy in a business as usual environment. And then if we add on a climate cost of energy, and that climate cost is the cost of mitigating against climate change. So it's battering off or fighting off the effects of climate change. We can add another big chunk. And so if we go business as usual, the direct core cost together with the externality costs, as they politely referred to, comes in at about 10 times the cost of switching. And really, if you kind of even half believe this, or even a quarter believe it, it seems insane that we should not be taking it to heart. So the guys, you can go and look up Mark Jacobson, Stanford, and you'll find that he's actually done climate models for 2050 for 143 countries globally, one of which it turns out to be South Africa. Okay, I'm going to switch now to showing a short video that I'm hoping is going to work. If someone can confirm that this is working.
We are on the cusp of the most profound disruption of the energy sector in over a century. And like others, this one is the result of a convergence of several key technologies, specifically solar photovoltaics, wind power, and battery energy storage. The cost and capabilities of each of these three technologies have been improving relentlessly for several decades. Just since 2010, solar has fallen in cost by 80%, and by 2030, it will be 70% cheaper than it is today. Wind cost improvements are also impressive, 45% since 2010, and another 40% by 2030. Lithium-ion batteries even more so, 90% just since 2010, and another 80% by 2030. Now, the consistency is easier to see when the same data are viewed on a logarithmic chart, and it's precisely this consistency that makes these trends so predictable. Solar and wind by themselves are now the cheapest way to generate electricity, and these are just global averages. The cheapest solar power in the United States, out west in California, is now less than 2 cents per kilowatt hour. And the cheapest solar combined with 4 hours of batteries is less than 4 cents per kilowatt hour. That's today. For context, here is how those numbers compare to the operating cost alone for coal and gas power plants. In other words, today, in 2020, it is already cheaper in sunny places like California to build a new solar power plant than to keep operating an old coal or gas plant. And solar plus batteries is not far off. By 2030, it's no contest at all. At those prices, nothing else can compete. And here's one other thing to consider about cost. Transmitting electricity is not free. In fact, it's getting more expensive every year. Now, you can't put a coal or a gas power plant on the roof of your home or business, but you can sure put solar panels up there. And by the late 2020s, there will be many situations where generation on demand, on site, is cheaper than the cost of transmission alone. That means that even if generating electricity at a coal or gas power plant were somehow magically free, rooftop solar would still be cheaper. We call this God parity, and it's coming. As their costs continue to improve, the adoption of solar, wind, and batteries is growing exponentially. Each of these technologies shows a beautifully consistent exponential curve. And this means that we're not facing a slow energy transition. We are facing a rapid and total energy transformation, and it has already begun. Now, conventional forecasts get disruption wrong. Major industry forecasts have made simple linear projections for the growth of solar, for example, year after year for 20 years now. And at the same time that disruption creates a new system, it also wipes out the old system. And this is not theoretical. This has already begun with coal in the United States. Year after year, these same industry forecasts have been desperately trying to save coal from collapse with wishful thinking. But coal in the United States has already been disrupted, first by fracking and now by solar and wind. So we have a disruptive technology convergence. The cost of these technologies are now so low that incumbents simply cannot compete. And that means that the disruption is inevitable. This particular disruption, the clean disruption of the energy sector, has already begun. And existing coal, gas, nuclear, and other assets will be stranded. No new investment in those technologies is rational from this point forward. So here's the trillion-dollar question, not just for the United States, but for the entire planet. Is 100% solar, wind, and batteries possible by 2030? To answer that question, we took real-world data for solar and wind power generation and built a systems dynamics model to determine exactly how much battery energy storage would need to go with it in order to meet 100% of electricity demand, all day, all night, all year round. We analyzed California, Texas, and New England as case studies, and we ran thousands of scenarios for each region. And what we found is that there are hundreds of different combinations of solar, wind, and batteries that could do the job. Yes, even in New England. Now, it's a balancing act. We can either build more solar panels so that we generate enough power even on short, cloudy winter days, or we can build bigger batteries to charge up ahead of time. But these combinations are not all equal. Some of them are much more expensive than others. So we then asked the next obvious question: what is the most cost-effective system? We discovered that the key to understanding how 100% solar, wind, and batteries is both achievable and affordable by 2030 is what we call the clean energy U-curve. The clean energy U-curve shows us that there is a cost optimal combination of generating capacity and battery capacity, a sweet spot. And for each region, it varies with climate and geography. But what is so surprising is where the sweet spot is located. It turns out that the optimal system will have between 3 and 5 times more total generating capacity than today's grid. Because with that much solar and wind, you only need 40 to 90 hours worth of batteries, and it's the batteries that are so expensive. Now, conventional forecasts have never even considered building 3x to 4x to 5x solar and wind capacity. But understanding disruption means rethinking the boundaries of the existing system. And the clean energy U-curve shows us that the least expensive combination of solar, wind, and batteries, these 3 technologies, is getting cheaper by the minute. And that's why this isn't just the cleanest system in 2030, it's why it's also the cheapest system that we can build. Okay, so what would this actually cost? Well, our analysis shows that if we start building now, California can have a 100% solar, wind, and battery system by 2030 for a total investment cost of $115 billion. Texas for $197 billion, and New England for $91 billion. Extrapolating this to the rest of the country, the total cost would be less than $2 trillion. That's $200 billion per year for 10 years. That's 1% of GDP for 100% clean energy by 2030. But there's more to this story than just a surprisingly affordable price tag. It turns out that 100% solar, wind, and batteries is just the beginning. This new system has a completely different architecture than the old one, so it works in very different ways. And perhaps the most counterintuitive aspect of this is that the new system produces much more electricity overall. So when we build a system based on solar and wind power, we have to design it to get through the worst times of year, those cloudy weeks during winter when the days are shortest. But by doing so, we naturally end up with the capacity to generate much more electricity on most of the other days of the year. And remember, this is still the cheapest electricity system that we can build. We call this unexpected benefit of 100% solar, wind, and battery systems superpower. Its implications are simply stunning. To start with, the sheer scale of superpower is enormous. In sunny regions like California and Texas, clean energy superpower output is greater than the total electricity demand today. And this pattern is consistent with other disruptions, where the new system is much larger than the old one that it replaces, like cars disrupting horses or smartphones disrupting film cameras. And what's more, clean energy superpower is not just available once in a while, it's available all throughout the year. Even here in New England, superpower will be available on 2/3 of all of the days of the year. And in sunnier regions, over 90% of all days. Now, because this superpower is coming primarily from the sun, it doesn't cost anything. There's no fuel. There's no additional wear and tear on the equipment. If the sun is shining, solar panels just sit there and happily make electricity. And that means the marginal cost of clean energy superpower is effectively zero. So just imagine what society could do with a huge amount of clean energy that is available almost every day and is essentially free. Well, the sky's the limit. That's enough energy to meet all of our water needs with treatment and desalination, for example. Or it's enough energy to electrify all of road transportation with plenty to spare. Or it's enough to replace fossil fuels in all residential and commercial heating. Or it could be used in recycling and waste processing or smelting. Or for the manufacturing of solar panels and wind turbines and batteries themselves right here in the United States, which of course would lower their costs even further. This superabundance of clean, ultra cheap energy will be transformative, socially, economically, and of course, environmentally. It will make communities healthier, it will create millions of jobs, and it will help mitigate climate change. Up until now, we've been right to conserve energy, to use as little as possible because of its harmful side effects associated with fossil fuels. But the new system architecture is not based on extraction of depletable resources. Conservation means the opposite in the new system. It's not harmful to use sunshine and wind, it's harmful to let them go to waste. 100% solar, wind, and batteries doesn't just clean up electricity either. Thanks to all of that superpower, we can eliminate virtually all fossil fuel use and the emissions that come with it by 2030. So what do we need to do to make this happen. Well, what we don't need are subsidies and carbon taxes, any more than digital cameras needed them to wipe out celluloid film. The disruption is already inevitable. What we need is leadership. We need communities and policymakers and entrepreneurs and investors to understand the future of energy and to act on this information by making the right choices today. Thank you.
Right, so we can carry on then. Thanks for bearing with me. I just thought I couldn't summarize the situation as well as what Adam Dorr from Rethink X did. So what I've done is had a quick look at the South African situation, and this is just to remind you of, first of all, globally, the reduction in capital costs of wind over the last 2 decades, the reduction in costs of PV over the last 2 decades, and the reduction in the cost of lithium-ion battery packs over the last decade and projections for the next decade. And as it was said, if you plot these on logarithmic paper, which all of our geochemistry friends would be very familiar with, we can see that we can get very clear predictions of where the costs are going to sit circa 2030. Now, I just want to look at where we currently sit in our energy system. This is 2021. I think this particular plot was for March, sometime in March. So it shows a week of demand curves, which are the red curves, and then it shows the build-up of how we meet that demand. Nuclear at the bottom, coal, Cahora Bassa is the dark blue, light blue is wind, yellow is solar, and then green is coming out of our pump storage. And the brown color that you can see mainly at the nighttime when the demand is lowest is charging up the pump storage. The gray is then gas. In fact, in South Africa at the moment, it's diesel, open cycle diesel turbines. And the little white gaps on this image represent potential load shedding. So that's an actual 2021 data set. With a build of how we currently meet, or rather don't meet, our demand requirements. In 2021 we used 231 terawatt hours. That was the demand, and the question then is, could we do 100% wind, solar and storage by 2030? Now, I'm not advocating, in fact, that we do 100% wind, solar and storage by 2030. And the reason I'm not advocating that is I don't believe it to be technically and logistically possible to build what we would need to build by 2030. And that's just because we no longer have our EPC construction capacity. I'm not sure that our ports are efficient enough to bring in the equipment, but I've done it theoretically by 2030, just to be able to draw a direct comparison with the studies that were done for the US. And then I'll show you that I'm actually advocating that we rather target 2040 for a complete switchover. So if, just to remind ourselves, if we look at California, the annual terawatt hour demand in California is 285. In South Africa, it's 231. The peak hourly demand is 63 gigawatts. Ours is about 34, or it used to be 34. I'm not sure that we can muster 34 anymore. We can demand 34, but I'm not sure we can supply it. And just something worth noting here is that our average to peak is much lower than the average to peak in California. And that's because we still have quite a big primary energy using infrastructure in South Africa. All of the mines and the smelters are primary users, and so they use consistent amounts 24/7. The big difference in average hourly demand and peak is brought about by homes, really, households. And in America, that peak is probably in the summer when everyone switches on their air conditioning. So the peak is often driven by people living in urban areas, whereas the average to peak differential reflects whether you are in a primary kind of economy or tertiary or quaternary kind of economy. But I've used California as a proxy for South Africa then in terms of the annual demand. Now, this is a very important diagram. I'll just take you through it very quickly. On the y-axis is the total capital cost of building a system. And on the x-axis is just multiples of the amount of generation capacity that one puts in. And that generation capacity is installed wind and solar. It turns out that it's mainly solar with lesser wind, but let's not worry about that at the moment. And what this particular diagram shows is that there's an infinite number of solutions to 100% solar, wind, and battery system that supplies electricity 24/7, 365. And those solutions are shown on that curve, that U-shaped curve. Each one of those dots is a potential solution. And in very simple terms, if you build less wind and solar, you generally have to put in bigger storage to be able to ensure that you never are short of supply. It's almost a case of interseasonal storage when you take it to the extreme. If, however, you overbuild, for want of a better word, wind and solar, and we'll show just now that it's not really overbuild, but if we overbuild wind and solar, we can reduce the amount of storage that is required. So as we move to the right on the x-axis, you'll see the battery costs are diminishing and the solar and wind costs are increasing. But the total cost drops rapidly as we increase the generation capacity, and then it levels off in a kind of a U-shaped valley and then climbs more slowly on the other side. Now, I have looked at I've got access to data for many years from Eskom. This is a wind capacity for 2019. It's all the wind data of all the wind farms in South Africa in 2019. But what I've done is I've shown a 24-hour moving average. So instead of plotting the raw wind data, I've plotted all of the wind data on a 24-hour moving average. And you can see from that it's never zero on a 24-hour basis. There's never no wind blowing anywhere over a 24-hour basis. But it's also quite interesting, if you look at it, it's bowed upwards somewhat into the winter months. So we actually get more wind energy in South Africa in the winter months than we do in the summer months. I've done the same for solar, which might seem a bit of an odd thing to do. I've looked at solar over 24 hours average. And the reason for doing that, it makes a much tidier graph. If you plot solar, obviously it peaks at midday and it's zero all of the night, and you just get a series of kind of peaks, I guess. Whereas if you look at a 24-hour moving average, you're actually averaging the solar over the nighttime and the daytime, but you're always looking at 24 hours. So that you're integrating the night, if you like, with the day. And you can see where it dips below that curve line would have been basically overcast days. And where it's sitting more or less on that curve line would be primarily sunny days. And you can see even on the overcast days, you're getting about a third of the output over a 24-hour period as what you would get on a normal sunny day. And that's because solar panels still produce, when it's overcast, about a third of the energy comes from scattered radiation. But the point to note here is that it's a concave curve. So you get less production in winter, and that's primarily due to two factors. There's fewer sunshine hours in winter, but also the sun angle on single axis tracking panels is at a less favorable angle in winter. So you've got a cos factor, which gives you lower output. So typically on single axis tracking PV systems, you would get maybe between 50 and 60% as much in the winter months as you'd expect to get in the summer months. And then if we add the two together, if we add the wind and solar curves together, we've still got a slightly concave curve, lower in winter than summer, but it's pretty close to a straight line if you look at it. So we have incredible wind and solar resources in South Africa, and we have very limited interseasonal changes compared to places that are further on higher latitudes than what we are. So we really do have world-class wind and solar resources, not just on a daily basis, but on a seasonal basis, and in terms of interseasonable variability. They actually balance each other out, with more wind in the winter months and less solar. So this is a clean energy U-curve for California. You would have seen from the video what the clean energy U-curve is. And there's a lowest cost point there. And what's very important to recognize here is that if you increase your investment by 10%, which is really just moving up on the y-axis by 10%, you'll see on the x-axis, it slides across from 3 point something to almost 5 times the generation capacity. And that's where you are not only able to have this superpower, which is automatically available because of surpluses that are generated at that lowest cost point, but you can increase the amount of superpower, and it's not linear. It's not a linear increase. A 20% increase in the capital cost will give you a much higher increase in the amount of additional excess energy that you can produce. So I've calculated a clean energy U-curve from South Africa. I sat with all the data from multiple years, and I calculated where the cheapest point would be for us to build a system by 2030 that would completely replace our current electricity generation system. That's coal, nuclear, OCGTs, the lot. I think I kept the pump storage and I kept Cahora Bassa in. The hydro from Cahora Bassa. And you can see there, and I've also changed the x-axis. So instead of using multiples of generation, I've chosen to use multiples of our annual demand. So when we're sitting at 1, it's 231 terawatt hours a year. And you can see we would go off scale here, because if we only built 231 terawatt hours of generation capacity from wind and solar, we wouldn't be able to have anything surplus to put into storage. And it's just, you don't get a solution, basically. So 1.5 here means we would generate 1.5 of our 231. 2 obviously would be double 231, so 460 something. But the so-called sweet spot for South Africa, the lowest cost on this curve, comes in at just over $70 billion. And it gives us 67%, 1.67 of additional electricity to what we currently have. Now, what's very important is if we added 20% to the capital cost of what we built, we could take our surplus from 1.67 to almost 2.5. And that's what I was saying earlier, is that it's disproportional, because this U-shaped valley is not symmetrical. It comes down quickly in cost, and then it tends to go up at a steady state. And in fact, your battery, the amount of batteries levels off. It comes down slightly all the time, but it more or less levels off. We need a certain amount of storage. And so if we're adding, then we're just adding the cheapest component, which is solar, and we're not having to add any additional. In fact, we're subtracting some of our storage, and you're then able to produce large amounts of additional energy at incredibly small amounts of additional overall capital cost. And that then generates the so-called superpower. And we'll talk about the superpower. Well, I am talking about it. And you can then read that depending on where you choose to build, you can see how much additional superpower. So if we go to 2, you'll see we're getting around about 231 terawatt hours of superpower, which is basically double our current annual demand. And I've plotted this as a table where we can see for annual generation capacity, 1.1, 1.3, 1.67. It shows us how much battery energy storage we require and for how many hours we require that. This is the number of hours. The battery is always the same. It's 35 gigawatts of batteries or storage, which allows us to be able to run the whole country, if you like, on batteries when the sun's not shining and the wind's not blowing. but we would require 100 hours of that. And the battery capex would make up 80% of the capex. We'd have very little superpower. And our total capital spend would be 185 billion. As we move down that U-curve then to 1.3, 1.67, you can see there's a dramatic drop in total capital cost, and there's a nice increase in superpower. And as we then, if we choose to do 3 times the amount of current generation, we're going to be producing a large amount of superpower, well over 400 terawatt hours of superpower. And we've only taken our total cost from 71 to 98. So this is what it would look like in 2030 if we built what I've modeled. That's what it would look like. We would need to build 101 gigawatts of PV, about 40 gigawatts of wind, and 35 gigawatts, 312 gigawatt hours of storage. And that's how it would operate. The wind and the solar would be in the daytime. The brown here would be going into storage. The green would be primarily coming out of storage at night. And the yellow here would be the so-called superpower, stuff that's not being stored. This would be excess power. But of course, by 2030, our load profile, which I'm showing here, wouldn't be the same as what our current load profile is. We'd expect to have seen electrification of transport. We'll expect to have seen generation of green hydrogen, about which there's much talk. We will have expected to have seen potential green steel manufacture with hydrogen instead of coal in steel production. So yeah, we would have plenty of surplus. So we would have 231 terawatt hours to meet our current demand, and there'd be 155 terawatt hours of superpower. And that, remember, is the sweet spot on that curve where it's built at the cheapest possible level. So this is just to quickly show you what my modeling tools look like. This is 2021, this is 2025, 2030. Of this model, I'm actually looking at going completely solar, wind, and storage by 2040. So you'll see 2021, 2025, 2030, 2035, 2040. So it's not targeting 2030, and the reason I'm not targeting 2030 is not because it would be great if we could do it, but because I don't believe we can do it logistically. I don't believe we can build quickly enough to do that. Notice that the capital spend is 93.8 billion, because we overbuilding now, and that we're looking at a electricity price in today's money terms of about 45 cents a kilowatt hour at the factory gate. That's before delivery. This would be the recommended annual new build up to 2040. The storage is shown as gigawatt hours, so it's the amount of storage capacity times the hours, which is why it's such a big chunk. This is the cumulative new build up to 2040. This would be the estimated annual capital cost. So we're looking at spending about $5 billion a year. And you'll see that capital cost stays more or less constant, although we're building more each year. And the reason it stays constant is because the price comes down, or the cost of building these things comes down more or less in lockstep with the rate of expansion of new build that I'm recommending. This is cumulative capital expenditure, and it ends up at about 93 billion. And then here's a proposed new integrated resource plan for South Africa through to 2040, which gives you the proposed build rates of wind, solar, and storage on an annual basis from 2021. I guess that horse is bolted already, or that ship sailed. 2022 is probably sailed already as well. This is certainly what we should have been doing and haven't been doing. But obviously one can adjust these dates and look at the impact that will have. And then just to finish off, this is an animation of the change, and it also shows the changing load profile. So in the future, our biggest load will be in the middle of the day, and that's when we'll be charging all of our storage facilities. And our smallest load will still be in the middle of the night. So that's just that animation. Thanks. That's the end of the talk. I think this will be made available, if I'm not mistaken, and there's all of my contact details. So, thanks.
Thanks, Clyde.
And I'm happy to answer any questions or discussion, enter into any discussion.
Okay, well, let's get the ball rolling, Clyde. I mean, it's all great stuff and in a sense, no brainer. Obviously, there are a couple of challenges, though. I mean, the one biggest problem that, and we've seen it in the minerals and mining sector, and the debacle about just getting a simple exploration strategy together. I mean, how do you deal with this dysfunctional policy environment to actually, get a process like this going?
The best way I can answer that is to tell the story over and over and over again until you wear them down. So the description is, it's like water on granite.
So
eventually one hopes that the weight of argument and the nature of the emergency that we currently find ourselves in will swamp and overpower the regulatory ineptitude.
Yeah, I mean, I hope that's the case, because it's pretty dire, but at least you're made of the same mold or substance that Paul Miller is on the sort of minerals mining side. Anyway, we've got some questions. Rob, do you want to start?
Hi, thanks very much, and Tar, thanks for the fascinating talk. Just a couple of points. The one thing about the costs going down, going forward, we all know that there's a huge problem looming with the supply of the raw materials for the new energy. And the mining forecasts and are that there's just no ways that we're going to be able to produce. There's no worldwide. So look, if South Africa goes along the path like that, that's fine. But if the world goes forward, we're not going to be able to actually supply the raw materials, and B, the cost of those raw materials will go up. So that's a problem from the cost forecast point of view, and also the time sort of period, because benchmark minerals, which have a pretty good grasp on this sort of thing, seem to say that we are okay till about 2025 as far as the forecasts going forward are putting in the new energy formats. But after that, we start the battle. So that's the first point. The second point is, I actually read two articles yesterday. The one was a study in California about the impact on bird life from wind and from solar, because apparently solar kills birds from the sort of heat that it generates above it. And they've actually found that what they did is they compared bird stats from before the new energy put in to afterwards, and they found there's actually quite a serious impact. I can't quote the figures now, but I remember one particular bird type species, they noticed a 20% drop, for instance. The second article was about the wind turbine manufacturers, where it appears that none of them are actually making any money at the moment. This all ends up with me. Look, I'm very positive about new energy, but I just can't see these forecasts being achieved in the time that we're talking about. And I also don't see that the cost is necessarily going to drop as the forecasts go. Tar, thanks very much.
Thanks. If you don't mind, I'll answer questions as they come in. I hate it when people say, let's have 5 questions, because then I've forgotten. So let's tackle the first one first. Most of the angst about supply of minerals has to do with batteries. I mean, there's obviously problems with steel for wind turbine masts, but let's focus on batteries. So I just want to say that although in the presentation I focused on lithium-ion battery packs just to mirror the study that was done in America, In South Africa, we've got lots of wonderful other opportunities. So I'm going to mention 3 other storage opportunities without, and if I've left anyone out, I apologize. So the one is to do pump storage in old gold mines. These fantastic opportunities of allowing the upper levels of old gold mines to flood and essentially form the upper storage dam of a pump storage situation, put in a penstock line down to a lower storage facility where we're pumping water out anyway. We have to pump water out of many of those old mines. What we're doing then is when the water flows back in, instead of letting it flow in willy-nilly, as it were, through fractures and things, we're focusing its flow back through a raised board penstock line with a Francis turbine in that. And people looking at this, Tyson Krupp and others, calculate that we can do up to 20 to 30 gigawatts of 10-hour storage in South Africa in old current and abandoned gold mines, particularly in the West Wits line, where we've got the overlying dolomites, where we've basically got, I don't know, 10 times the size of the Vaal Dam sitting underground. So that's one example. Another example is taking old tailings dams and turning them into composite blocks that each weigh 35 tons or so, and then lifting and lowering those blocks in a structure using 100-year-old lift technology, taking the blocks from the bottom to the top of a structure, wheeling them along little caster iron things like when you put your suits in your cupboard, but I can't relate to that because I've only got one suit, but you know what I mean. And you stack them along. And then when you want to get the electricity back or the energy back, you wheel those things along and lower them in the lift again on the boundaries of that structure. So that's another form of energy storage. And then, of course, there's flow batteries. And one of the key flow batteries is vanadium flow batteries, and many of you will be aware of Bushveld Energy and the fact that we can use vanadium flow batteries to do it. So that partially answers the question. To take it a little bit deeper, some of the things we need are things that haven't been needed previously, and we're still mining them as if they were tier 4 minerals. And we all know it'll take time, but if we start looking to mine some of these elements as if they were tier 3, tier 2, tier 1, etc., we will be able to catch up and do them. So I think copper is a good example. Start off with high grade, small mines, end up with massive porphyries, mining grades of copper that would make you question whether they would be profitable, and yet they are. And the same thing will happen with the likes of some of these exotic things like lithium, etc., where it'll take a while to catch up, but catch up they will. And if the prices continue to increase in some of these elements, as they've done now with various wars and COVID and thing going on, the manufacturers start swapping out. So you'll remember back in the 80s when the Hunt brothers chased up the silver price, that was the death of photography back. I like to trace the death of film photography back to the Hunt brothers in the 80s. So I don't really fear that we will have a shortage of the elements we need. The mining companies will step up to the plate and the manufacturers will find ways of using less. Just quickly to get to the bird story, the solar that kills birds, you're quite correct, but it tends to be solar thermal, not PV. And solar thermal basically has got cut off at the knees by PV. So solar thermal was cost competitive a while ago, and then PV came along and stole the show, a bit like VCR stole the show from Sony Betamax. And so stories of scorching birds above solar fields refers to a concentrating solar where they focus sunlight with mirrors on central towers. That's the first point. And then the second point is with regard to bird life and wind turbines. I haven't seen the latest figures, but I think, first of all, domestic cats kill something like 1,000 times more birds than wind turbines. The second one is just tall buildings that birds fly into. Of course, motor vehicles, on anyone who's driven along the road will see. The sad thing, though, is that there's some particular birds that get affected by wind turbines that may not as often fly into buildings, for example. And that's why during the environmental impact assessment, one tries to build wind turbines that are certain distances from vulture roosts and that kind of thing. But yes, there are inevitably deaths, but I can promise you, and this isn't an excuse, there's a lot more just from stationary buildings and from motor vehicles. It's not even close. So it's a very serious issue. And there's some interesting research done. The guys have seen if you paint the turbines black and white in a sort of checkerboard pattern, it makes the birds more alert to them. And they've done, so these various things one could do. I think that addresses the questions that were asked. And obviously, from a mining perspective, when one talks about shortages of necessary materials, one would hope that those that think they have the capability of supplying those materials, one would hope that their eyes would light up at the prospect.
Sorry, can I?
Thanks, Clyde. Before you take on Willem de Meyer, Klaas wants to know what adjustment cost to the distribution system is required, and has it been factored in?
Okay, so just to split that out, we have what we call we've got a transmission system and a distribution system, and the switch from one to the other is basically the voltage. But I like to think of the distribution system as inside the meter, inside local municipalities. So it's like distributing to you in Overberg or in Cape Town or wherever. In the transmission system, there's a lot of sub 132 kV lines that are technically called distribution, but are still serving the function of transmission, if you see what I mean. So it's gone from 400 kV to 132 kV, but once it gets into the cities, it's down to 22 kV, 11 kV, and by the time it gets to your house, it's 240 volts kind of thing. So when you say distribution, I'm going to assume you mean the distribution of the electricity on a grand scale, not necessarily the last 10 kilometers of distribution within the cities. And the answer there is that those studies that were done in America specifically assumed there was nothing done to the transmission system. That lowest cost point was placing stuff close to load areas where nothing had to be done to the transmission system. They then said, if we were to strengthen the transmission system, and if we were to place the storage facilities at the most suitable spots, the costs would drop even further. So they did it with the assumption of no major reinforcement of the grid system. And I think anyone can see that. Let's just take a silly example. You've got a solar plant that can evacuate 20 megawatts because of the line restraint. But you put a battery with it, so it can now evacuate 20 megawatts in the daytime, and you can have a 40 megawatt solar plant, and it can evacuate another 20 megawatts when the sun's got down on the same lines. So you can actually triple the amount of current that flows across the lines if you carefully place your battery storage without having to put in any more transmission. So it's a very important question, but it also only adds about putting in additional transmission is actually relatively inexpensive, but it's a time constraint because it's time to do EIAs, time to get servitudes, time to fight with farmers about putting a new line across their field. But the short answer is the study done in America, which I then simulated for South Africa, assumed zero increase to the transmission grid. Thanks.
We can now get Willem de Meyer. You can open up your mic and ask your question, Willem.
Thanks. Hi, Clyde. Yeah, thanks for an interesting talk, as always. Good to see you once again.
Yeah, I was a bit scared when I invited you, Willem, because I know your background, and I thought, here comes the gas man.
No, it's an easy question. I just wondered if you'd given any thought to or try to estimate or forecast the surface footprint that would go along with installing this capacity for solar, for example, Of course, the associated, as was mentioned already, the associated issues related to environmental approvals and fighting with farmers to put these large installations on their lands.
Thanks, Willem. Well, I haven't done a recent footprint calculation for my extreme 2040 case, but what I can tell you is that it's less than one. It's wind and solar combined are significantly less than 1% of South Africa's land space, significantly less. But the thing that's of most interest to me is that it's significantly less than the footprint of the current coal fields in South Africa. So if one just took the mining of coal in South Africa and looked at the size of that footprint, you know, whether you want to look at it from an open cast mining or an even underground, where you sometimes render surface not suitable for certain other usage because of checkerboard collapse or underground burning of coal or whatever, the surface area would be significantly less than the surface area currently underlain by active and past coal mining activities. Another interesting study I did is if I looked at the exclusion zone around Vaal Pit, where we dump nuclear waste. The exclusion zone around Vaal Pit is big enough to supply all of South Africa's solar energy. But one wouldn't do it all in one spot like that, because obviously the infrastructure wouldn't be there to evacuate it. But just the exclusion zone around the nuclear waste disposal site in a nice sunny part of the country would be big enough to power all of South Africa's solar needs. So the footprint, I like to think that the best way to do the footprint is a lot of rooftop solar. So the solar I was talking about wasn't restricted to utility scale. A lot of rooftop, parking lots, these all sorts of things. But I quite like the idea of having groupings of quite large wind and solar in places that make sense. So these parts, for example, there's an area, I don't want to give away trade secrets here, but the western part of the Eastern Cape, where it sort of abuts with the Western Cape and the Northern Cape, is a so-called renewable energy development zone, round about south-ish of Beaufort West, just to the west of the plains of Kamdaboo. There's unbelievable wind and solar resources there, and it's also where these very strong transmission lines that have been built and are being planned to go down to a potential nuclear power station at Tastepunt. And so it's a pivotal point, and we could probably put in 10 gigs of solar and 10 gigs of wind and 5 gigs of storage clustered in a spot like that. I'm not suggesting we do that, but it doesn't have to be distributed across the whole landmass. You obviously do it where it's useful. What I have found interesting, Willem, in terms of a slightly different note, is that in most of my modeling, the ratios of solar to wind to storage come out as about 853. So 8 gigs of solar, 5 gigs of wind, 3 gigs of storage. And that appeals to me because it just so happens to be the Fibonacci series. So if anyone can vaguely remember the Fibonacci series, 853 are 3 members of the Fibonacci series. And I was quite thrilled to see when the International Energy Agency brought out 2050 forecasts for wind, solar, and storage. So help me, they were exactly in the Fibonacci ratio for the globe. So that, I don't know why, it just gave me a level of modeling pleasure. If one can ever get pleasure from modeling. But thanks, Willem.
Annie, are you going to do the next one? There was Clyde, I don't know if you can see the chat group. Thanks, Clyde. Any comments on the efficiency of vortex bladeless turbines versus current blade turbines?
I don't know much about that. All I know is that in my endeavors over the last 10 years, I've got involved with about a dozen startups CSP, CPV, dual axis tracking, and all coming out of the States, US. I used to visit there regularly, at least once a year, and all of them chopped off at the knees by the cost of solar. So as solar photovoltaic became cheaper and cheaper, so many of these other technologies got chopped off at the knees. And I'm backing solar at some point to chop wind off at the knees as well. The reason it won't chop it off completely is obviously because the sun doesn't shine at night. But I'm sure there are developments. I've also seen dual blade turbines advocated now for very high wind areas, probably for offshore facilities, where you have a twin blade instead of a triprop. But those other ones, if they come along and they're less expensive and more efficient, bring them on. But I don't know too much about the comparative analysis. It's better often to look at what are people installing at the moment, and if they're as good as they say they are, why aren't they there already at scale? That would be my sort of simplistic answer.
And Clyde, just going back to my original sort of comment on the whole policy environment. I mean, who is driving, the whole system? I mean, do Eskom and raters and that, are they involved?
No, the big disconnect is that Eskom don't set the new generation policy. Yeah. So Eskom are tasked with keeping the old fleet running. And if it's not running, they get grilled every 3 months, either by the media or by parliamentary scoper committees or whatever. So their job is to keep this old coal fleet running. And, the analogy I like to use is you can't skip maintenance and then catch it up. It's just actually not possible. So any talk of catching up maintenance. So the analogy I like to use is you're meant to, at my age, go to the doctor every year for an annual checkup. And you can't skip 5 annual checkups and then go to the doctor 5 days in a row and think you can catch up. It doesn't work like that. You will have missed things. And when you then do try and catch up, to your horror, you'll find that non-wearing parts have now worn out because you haven't replaced the wearing parts. And my experience at a young age of 22 of being a mill superintendent at Falconbridge, if it taught me one thing, it taught me about mechanical maintenance and relining mills and crusher and everything. And if you skip the preventative maintenance, or if you don't change the parts that are meant to be wearing parts in time, you start wearing out the non-wearing parts. And that's when the whole game changes, I'm afraid. And so the disconnect is that Eskom aren't in charge of procurement of new energy. That falls under the Department of Minerals, Energy, Resources with Gwedi Montash. And it's horrifying to realize that it's 8 years since the last official procurement has resulted in the building of a wind or a solar farm, which is currently running. So there was an 8-year, it was 2014 when the last bid window was run that has resulted in something that's finished and built now. And the subsequent ones haven't even reached financial closure yet. So there's been an 8-year gap. So there's a silver lining to that. In those 8 years, you will have seen the cost of wind and solar and storage has come down tremendously. But, it's like the laptop syndrome. If you don't buy a laptop ever because next year's one's going to be cheaper and faster, there's an opportunity cost that you lose by not having been able to make use of that laptop. And you get to a point where the saving that you might make is wasted. So we're in a crisis at the moment. I mean, we should have the president at 8 o'clock tomorrow evening coming on and saying there's an energy crisis, there's an emergency, and I'd rather call it an emergency now than come on in 6 months' time and talk about a disaster. And so I don't know how one can get that message across. I certainly try, but it's really, really serious now. Half the coal fleet not working and the other half running at risk. Just think about that.
No, Clyde, I mean, that to me, and I think we're talking to the converted here, is exactly the problem. I mean, our presentations on Zoom have shown exactly that, and we listened to you today. I mean, the talent and the experience in this country is just frightening. But it's not being, it's not being embraced, and you don't see a working group to actually work through some of these things and get the process underway. I mean, the Western Cape government obviously has been talking about, doing exactly that, going off grid and looking at local energy sources and wind and so on. But, even that's been very slow. But unless, unless there's a big shift in the whole policy development environment, and 8 years is a tragedy. There's a lot gone wrong in that period, and it, right now it looks to be getting worse.
I'm currently focusing on 3 groups: communities, trade unions, and financiers. One of the reasons the trade unions are anti, they're actually not anti. Some of the trade unions were the first to call for switches into renewable energy, but they wanted the ownership to be more widely distributed and more democratic. They didn't like the fact that European IPPs were sort of ruling the roost, as it were. The communities that live in the pollution plume of the coal mines and the coal power stations, some of the saddest experiences of my life are speaking to them when the people who grew up in those areas can't get jobs at the coal mines and the power stations. And I said, why not? And they said, because they failed the medical exams. They can't flip and blow the breathalyzer. Now, you know that if that doesn't bring tears to one's eyes. So I believe that we have what's referred to as a wicked problem. We can't try and solve any one piece of the puzzle on its own. We need to look at a multi-solution. We need to solve the cost of electricity to the poor. We need to solve the reliability of the electricity to the mining and smelting and other industries. We need to democratize the ownership of this new fleet. We need to have municipalities who don't pay their bills, but there needs to be a solution to do that. And that's perhaps what I'll cover when I give my second talk, is how we go about enacting what is so clearly the right thing to do. And so I spend a lot of time at the grassroots level, but also at the financial structural level, because ultimately this thing comes down to finance. And I mean, in very simple terms, if you took 100,000 Rand loan on your bond, invested it in a green bond that built a utility scale solar plant that delivered electricity to your town, the electricity price for your town, this local municipality, would drop by about 50 cents a kilowatt hour. You would get a better dividend from your green bond on that solar plant than you currently get from Alan Gray, with apologies to Alan Gray. And you would be able to further subsidize the cost of electricity to the poor. And you'd be able to give the green credits to businesses who needed green credits for export reasons. Citrus farmers, ostrich meat farmers, if they don't have green credit, sharpish or lower carbon footprints, they aren't going to be able to export their products into global markets. So that's what I'm working on, but it's done at a scale of it needs to involve the whole country. And I think if you go to the levers of the finance, and I'm talking here about the local banking industry and the local pension fund industry, the local investment industry, in my opinion, they hold the key. And they need to see there needs to be a disruption to the way in which these things are financed, in the same way that they are currently disrupting business as usual in the energy production.
Yeah, and I agree with you, Clive. I mean, I think it's got to get back to civil society. I couldn't agree more. You know, the financial sector has a huge role to play. I mean, it's very disappointing to see what's gone on in the stock exchange and how many companies we've lost. And the other side I find disappointing is big business and our professional societies, you know, including the MC, the Mining Council. I mean, where, you know, I mean, all of this affects them. You know, and we know the mining companies are ready to go green and do their own solar systems and so on, but you know, you just don't see a real driving voice there. Anyway, that's for another discussion, and hopefully we can pick that up on your next presentation. Any last questions, and then we'll wrap up. Henny, back to you.
Thank you very much, guys. I think it's time that so there's one more chat here. People just saying thank you very much. Have you looked at the chat box? Everything's fine. Next week, we listen to Jock Harmer talk about the new trends in clean energy. Hope to see you all back here and more of you. Thank you.
Thanks, everyone. Thanks very much, Clyde. That was excellent. And thanks to everyone that pitched this morning.
Thanks for the invitation. I shall have to pay a visit sometime to check the terroir or whatever of the region.
We're waiting. We'll pay your services then as well.
Right.
Pay in kind, Clyde, so come down and join us.
I'd like
Bye, everybody.
Cheers.